So I hope you are eager enough now to get to know what kind of topics are coming up in this semester. So what is the topic of this course here? Well, first of all, maybe some of you or most of you attended the KDDM course by Matthias Renz. And if you did that, then you may recall that the focus on this in this course was on how to identify and solve specific data mining tasks. Yeah, but very simple ones. So the KDDM content is about basic data mining and basic machine learning methods for the typical data mining machine learning tasks, which is unsupervised or supervised learning, supervised learning or unsupervised learning tasks. So frequent pattern mining, unsupervised, clustering, unsupervised, outlier detection could be unsupervised or supervised. In the supervised case, it's more an unbalanced classification problem, typically classification regression that is, of course, supervised. Sorry. So what you actually get is a large toolbox of methods for solving those problems in those categories here. Yeah, so for solving those data mining and machine learning tasks, and those methods are typically very good for learning in well-structured data and of small to medium size. Yeah, but not so well for not or semi-structured or unstructured data, and of course also for big data. We have the lecture on big data management and analytics in the winter term, which takes care about what happens if we have really huge data, big data. Yeah, but we don't have something where we just say, okay, medium to small data sets, sized data sets, but unstructured, complex structured and stuff like that. So we don't have methods for that, and spoiler, that will be the content of this course, of course. Yeah. Anyway, be clear with all these methods you got to know in KDDM, and we'll have a short overview, of course, of those. With this toolbox, you can already do really a lot. Yeah, a lot of fancy things can be done. So don't underestimate that. On the other hand, you cannot do say the specific things. Yeah, so the toolbox is mostly about just the basic methods for well-structured and small to medium-sized data. So the potential limitations, of course. So once again, a big asset to have this toolbox, but of course there are limitations, potential limitations. So what is the purpose of advanced data mining and machine learning methods? Well, almost all of those methods from KDDM work on structured data, meaning typically they use the representation of feature vectors as canonical data representation, which is perfect, yeah, because very often you can just transform any kind of data into this canonical representation of feature vectors. It's basically a table of columns where the columns have integers or floats, typically, yeah, doubles, as data types. And very often you can just transform any kind of data in this kind of canonical format or canonical representation, feature vectors. And then you can just apply those methods from KDDM to learn something out of it. That's the beauty and that's the mighty, so to say, of this toolbox you learn there. Yeah? And of course, similarity distance measures play a very important role in those methods from KDDM, but we actually don't discuss them too deep there, or only simple distance measures are somehow implicitly used. So this is not a big deal, not a big topic. And for complex structured data, of course, as I just said, we can do implicit or explicit feature transformation. So by hand, or maybe even learn the representation through deep learning approaches in order to get this canonical representation. Yeah, and that's exactly the beauty of this canonical representation. Yeah, but nowadays, of course, the complexity of the data is ever increasing, and that has some bad consequences. Meaning, for example, that those feature transformations, implicit or explicit, so explicit feature transformation, implicit kernels, are very often not so easy to find, or is a kind of intellectual challenge on its own. Yeah? So we talk about scenarios where this is not too clear, or what kind of similarity measures, feature measures should we use actually. Yeah? Very often also this canonical representation of feature vectors, which are basically tables, yeah, is just too simple to actually model all semantics, all aspects of the object semantics. Yeah, that is a kind of open and very, very old discussion where we can compare the relational table model versus the object model, which is a graph structured model, if you want to think about that. Yeah, so tables versus graphs, which is which is more expressive, so to say. Yeah, and of course graphs, object-oriented model, you can model much more much better complex semantics of objects rather than in the relational model where we use tables. Yeah? So in that case, the canonical representation of feature vectors is probably not that what you really want. Yeah? So then you have to split the information in multiple tables which are connected to each other, but you cannot handle that in a reasonable way with the toolbox from KDDM. Yeah? With the canonical representation is just one feature vector table. Yeah? And third, sometimes also representation learning is not applicable. So you may think, well, okay, then let's make the deep learning stuff. But the deep learning stuff requires typically a lot of data, a lot of training data, such that it makes sense. And very often you don't have that. So in that case, representation learning is also not applicable. There may be other scenarios where it's also not applicable. So deep learning is not, as we say in German, the eierlegende Wollmilchsau. So it's not the, what is it? The pig that gives eggs and milk and eierlegende Wollmilchsau, whatever, and maybe also wool. I don't know. Yeah. So it's not the one fits all solution like feature vectors. Feature vectors are also not the one fits all solution. So there must be something different or there must be something there which can be applied if those two very general approaches, feature vector representations, representation learning with deep learning, fail or cannot be applied. And that's exactly more or less the topic of our lecture this semester. Yeah? So how to deal with data complexity then, if you cannot convert these complex data into feature vector representations, or you cannot learn that from deep learning approaches, from neural networks. Well, you can of course design specialized approaches for different data formats and different data structures, different data complexities, which is of course not that hasn't that beauty of a canonical representation, because then you have very specialized approaches and very specialized solutions, but that's how it is. Sometimes specialized object complexities require specialized solutions, so to say. Yeah? You can also, of course, try representation learning as a kind of transfer learning problem. Yeah, so that you use predefined things, pre-trained networks, and try to transfer these pre-trained networks to your problem. But that usually doesn't work too good for small and medium data size set. Of course, for other domains, for images, for example, transfer learning typically works pretty fine. Yeah, but in that case, yeah, so very often you can't do that. So the lecture is mostly about how to handle different data types with specialized approaches. The first point here, yeah, and not primarily, at least primarily, about representation learning. Yeah, we'll probably strive also a little bit deep learning here in that course, but you probably know that there is a course on neural networks and deep learning this summer semester also by our colleague Mr. Meyer. Yeah? We don't want to interfere with that. There is a specialized lecture on that. Yeah, so we may strive that a little bit, may glance that a little bit also here. We did that already in the winter semester, or do that already in the winter semester about big data. There, it's, I think, somehow a canonical thing. Yeah, because if you have big data, then per se, and unstructured data per se, that is something where neural networks, deep learning may work. Here we focus on scenarios where deep learning typically doesn't work, and also transfer learning doesn't work. So we need, in order to somehow get a hands on this data complexity, we need specialized approaches. Yeah, so that is the purpose and the content, the main focus of this lecture here. So where does data complexity comes from? Well, very shortly here, we will talk about high-dimensional data. High-dimensional data is still feature vectors, tables, but they have their own problems. So we will talk a lot about high-dimensional feature spaces, feature vectors actually. So it's still feature vectors, but we think it's complex because high-dimensional data has very, very specific problems. We'll talk about time series. But medium-sized time series. We'll talk about sequences, spatial temporal data. So all that things have some kind of sequential nature in the data. Time sequences, not time sequences, but general sequences. Spatial temporal data is sequences, time sequences in a spatial, in a geo environment. So all those things are sequence stuff, so to say. We'll also talk a little bit about graphs. We probably won't talk too much about text and shapes, but that may be also a very good example for data complexity. And the main thing is that data can often no longer be modeled by just plain tables, feature vectors, or by without losing important semantics, or only by very high-dimensional feature vectors, and they have their problems on their own, which we'll talk about in one of the next lectures here. So to round it up, a short recommendation on literature. Here is a very general, some very general textbooks for data mining, machine learning from different perspectives. So from the data mining community, from the machine learning community, from the pattern recognition community. All those communities somehow contribute to learning from data, and if you want to dig in a little bit deeper, those are my recommended textbooks, and we will probably give you also some textbooks through the individual lectures, because some of the lectures or some content is really up to date, and can only be read in the original papers, and we'll give you the original papers, at least the reference to these papers, of course, at the corresponding times or locations. Okay, so that's it. That's it also for this week. That's the good news. So we'll really start off next week with a kind of recap of KDDM, but it's not really a recap. I really try also to add some more things into your toolbox box. So if you have attended KDDM, it's, I hope so, at least still worth to have a look in this one. If you didn't, then it may be a little bit short with the basics, but I will add a little bit in more details, also more to this toolbox, and all of these methods from KDDM are also explained very good here in these textbooks. So in the end, if something is unclear, remains unclear, I have to reference or point you to these books here, but I hope it's not too bad actually anyway. Okay, so as once again, that's it for this week. Next week we'll start with the introduction or the basics, and hope to see you there.